So thank you very much for the introduction and also for the invite to talk at this meeting. Indeed, we are having this meeting today as an online meeting because of COVID, and that's also what this talk is about. So to limit the spread of the coronavirus, policy measures have been taken or put into place throughout the world in almost all of the countries, starting in the beginning of 2020. So here you see how these measures, that are the darker the colors you see, the more measures have been taken, were quickly implemented in February, March of last year, and are still in many places in place. And these measures, these policy measures, they have a very big impact on the way that we live our lives, the way that we can travel, the way that we do our work, our economies, etc. And because of that, it also has an impact on our emissions, the anthropogenic emissions to the atmosphere. And in turn, that has an impact on air quality and climate. So in this talk, I will talk mostly about nitrogen dioxide, or NO2. And NO2 is a trace gas, it's a regulated pollutant, and it's a precursor to ozone and aerosols, which are the main components of smog. NO2 is emitted by humans mostly through the burning processes of fossil fuel and biomass. And the main sectors that emit are transportation and energy and manufacturing. And in the world map, you can see in blue those regions where transportation is the dominant NO2 source, and green is where the manufacturing and industry and energy sectors are dominant. NO2 is short-lived. It lives only between 2 and 12 hours. And that means that there is quite a direct link between the concentrations that we observe and the emissions. What's also important to mention is that because NO2 is emitted through the burning processes, there's also a link between NO2 and CO2. They are co-emitted, and as such, NO2 can be used also as a proxy for CO2 emissions. Now, NO2 can be measured very well from space. It has been measured almost since the beginning of the 90s. Today, I will show data from the TROPOMI instrument, which is an imaging spectrometer that was launched in 2017. It is an instrument on the European Copernicus Sentinel-5 satellite. It has daily global coverage and also a really good spatial resolution of about 5 by 5 kilometers. So here you see 3 images from the TROPOMI instrument. On the left-hand side, you see an image of NO2 over India and Pakistan, and you see these plumes of NO2. These are from power plants and from cities, and they are transported over the sea. You can trace these plumes over a couple of 100 kilometers. In the middle panel, you see natural emissions. In this case, it's SO2 from the Etna volcano, the freshly produced plume, and the plume from the previous day. And on the right-hand side, you see the methane plume. This is from a leak from an oil and gas facility in Algeria. Now, when you take these individual observations that we do every day, and you put them together into a yearly mean, you get a global image for NO2 that looks like this. So this is the mean tropospheric NO2 for the year of 2019. And you can see that the concentrations are especially high over the highly densely polluted regions in Southeast Asia, where there's also a lot of manufacturing industry ongoing. But also in other places, in India, in Europe, and in the US, you see the highest concentrations in the densely populated regions. And there's a tremendous amount of more detail in these images. If you look carefully, you can follow the shipping lanes. So these are caused by the emissions of NOx by the big ships sailing our oceans, so the tanker ships and the very large cargo ships. Now, what's intriguing about the NO2 concentrations is its very short lifetime, as I already said. It lives only between 2 and 12 hours, which means that if we would stop all anthropogenic emissions today, this image would go dark in a few days. And there's a very direct link between the emissions and the concentrations. And this is also very useful when it comes to the analysis that we have done for the COVID-19 cases. So for the COVID cases, there are 4 main methods that have been used to analyze the data sets. And they are here sorted in order of increasing complexity. So the first way that you can do is you can just compare the NO2 concentrations during the lockdowns with a reference period just before. You can also compare with the concentrations with a reference period that was, for example, last year, or the average over a couple of years. Well, these methods, they of course do not take into account the variability through, for example, the meteorological impacts on the lifetime of NOx. Then we can also correct for the effects of meteorology and compare the concentrations. And the most complex here listed is when we do an inverse modeling of the emissions. So we calculate back what the emissions were using model information and then analyze the trends. And all of these 4 I will show in the course of this presentation. Now, last year you probably have seen in the media some of the tropomi data that we measured. The tropomi NO2 data have been shown, I think, in all major news media around the world. And what was interesting to see is that, well, a lot of the analysis that were shown were okay, but we also saw analysis that were not properly done. Because you have to take into account the effect of meteorology, you have to be very careful about how you treat the data. But because all the tropomi data are free and open, which I'm a big fan of, also gives access to people who may not have the background to do this kind of analysis. So I think the bottom line here was that it's important to have trained professionals to do the analysis to really get the right information from the data. Now let's go back to the beginning of last year, of 2020. So these 2 maps, they compare the period in 2019, in February and March. On the left-hand side, on the right-hand side, we have a period in 2020. And you can immediately see in this image the very large impact of the COVID-19 measures in the reduction of the amount of NO2 measured by tropomi over China. When we look over Seoul, we see that the reductions are much less, and that's because the policy measures that were taken in this period were not as strong in Seoul as compared to the measures over China. When we look 1 month further in the March-April period, again it's 2019 on the left side, and on the right side is 2020. We see that the concentrations kind of were much higher. So already in March and April, when the rest of the world still had to go into lockdowns, the Chinese economy and the Chinese started to work again, and that has been so ever since. And we can do a further analysis on this. Now, this image is based on an inversion of the emissions, so taking into account all the meteorology and such. And you see the period from 2019 and 2020. And here in the vertical red lines, you see the moment of the Chinese New Year, which always results in a dip of NO2 because of the factories closing down in this period. But you can see that over 2020, this dip was way deeper and also way longer than in 2019. But you can also see that the NO2 concentrations increased quite rapidly after this lockdown period in March. Now, moving on to the rest of the world. So this shows comparisons, differences between 2020 and 2019 for different regions in the world. For the US, Europe, and India, these are for April, when in many cases, for many countries, the most severe lockdowns were in place. For China, this is the month of February, because the lockdowns were earlier over China. And what you see is that in India and in Europe, you can see everywhere these blue colors, with some exceptions in Russia, indicating much lower concentrations than the previous year. Over the US, it's much less clear, but if you do the zoom into the New York and large cities over the West Coast, you will also see a similar decrease in NO2 concentrations. You can see that even better when you look at time series. So these are time series of a large number of cities, urban regions throughout the world, covering the January to June period. And in black, these are the concentrations for 2019, and in red, these are the concentrations for 2019. And the gray areas, they indicate the periods of the lockdowns, which, as you can see, varies throughout the different cities. But I think the take-home message is here that in all of these cities, you will see decreases in NO2, which range from 14% in Sydney to over 50%, for example, in India. And we see this through all the cities in all the continents. What's also important is to compare our data with what has been measured from the ground, because of course there are in many cities also ground-based networks from which we can do analysis for. And in this case, I'm showing you in the top row the Tropomi data, again black 2019, red 2020, and in the bottom this is the surface NO2 analysis. And overall, there's very good consistency between the reductions that we derive from space and what we derive from the ground. So that is very consistent. As I said in the beginning, one of the importance for looking at NO2 is its role in tropospheric ozone. So it's a precursor to ozone as well as to aerosols, but here I'm looking at ozone, and because we see these very large changes in NO2, you would expect also changes in the ozone levels. And what we see is that over urban areas, we see an increase in ground level ozone of 6.4 plus or minus 11%, whereas in the free troposphere we see a decrease in tropospheric ozone. Now this may sound like contradictory in the beginning, but the response of ozone to changes in NO2 is very nonlinear. If you are in a very urban region, you would expect that if the NOx levels go down, that tropospheric ozone would go up, as we find also in the data. Whereas in the free troposphere, you would expect the opposite. When NO2 or NOx goes down, you also expect ozone to go down. So this is also consistent with what we expect. Now, a short look at other gases. In this case, I'm looking at India. In the top row, you see April 2019 concentrations, and in the bottom, you see 2020 concentrations. And you see NO2 and then SO2 next to it. And you see that the SO2 concentrations, they also reduced quite consistently with how NO2 reduced over India. That also indicates, because a lot of this SO2 comes from power plants, that the power generation was reduced during this period of the lockdowns in April. Now going further, we see a CO that is very difficult to analyze because the CO lifetime is much longer, and there's also a larger number of sources. So that analysis is not very, we cannot draw strong conclusions from that we've seen decreases in CO. And we have formaldehyde and glyoxal. These are gases that have, these are VOCs that are quite difficult to measure, but still over northern India, we do see reductions in formaldehyde and glyoxal that we think are larger than the interannual variability that we may expect. So that's just on the edge of what we can detect. So to conclude, the satellite data that we produced with TROPOMI, they have been used extensively to report on the changes due to the COVID-19 lockdowns. They have been shown in many of the major news media around the world. There are many publications using the data. There's one warning there that we've seen analysis that have not properly done. It really needs trained scientists to do such analysis when you compare different periods. The reductions that we find over the urban areas, they range in the order of 14 to 63% during the lockdown. So that's really a lot. A lot of that can be attributed also to the reduced traffic in these periods. Well, the changed emissions, they have effects on tropospheric ozone, and these are in line with what you would expect with an increase in tropospheric ozone over the very polluted region and a decrease in the free troposphere. And the effects on other radioactive gases, they are far more complex because of the chemistry that's more complex for these gases, as well as due to the larger measurement errors and the longer lifetimes of some of these gases. And if you're interested in more information, please send me an email or visit one of our websites where you can find all information about the TROPOMI data and how to get it and how to use it. And with that, I would like to thank you and would be interested in taking any questions.